Dear students, this lecture is about the complex numbers. You have already studied in first year that what are complex numbers. We are not going into the details, but we are going to take some certain topics which are necessary for you people. So let us start the lecture. That what is complex number and the corresponding complex matrix. Complex number is the number of the form a plus b iota. A plus b iota denoted by z. Complex number, this is a complex number, and which is denoted by z. So z is equal to a plus b iota is called a complex number, where this a, the first part a, is called the real part of this complex number z. A is the real part of z, and the real part of z is written as Re of z. So Re of z means real part of z, and that b along with iota is the imaginary part of this complex number z, and imaginary part of z is denoted by Im of z. Im of z means imaginary part of z, with the property that iota is equal to square root of -1. Iota is the square root of -1, and squaring both sides to get iota square is equal to -1. So along with this property, this number a plus b iota is called a complex number. There are certain notations for complex numbers. Two of them are popular to use. The first one is the ordered pair notation, and the second one is iota notation, the equivalent notation. For example, if you write 3 plus 4 iota, so 3 plus 4 iota is in this notation. We can write this complex number in ordered pair notation as 3 comma 4, real part comma imaginary part. This imaginary part will be written here without iota. So whenever you write a complex number in ordered pair form, you need to write those two components, the real part and imaginary part, comma between them, but iota will not be written in with the imaginary part. Similarly, -1 plus 2 iota can be written as -1 comma 2. 0 plus iota can be written as 0 comma 1, or we may say that 0 comma 1 can be written as 0 plus 1 iota. Similarly, 2 comma 0 can be written as 2 plus 0 iota. 4 comma -2 can be written as 4 plus -2 and 2 iota. So these two are popular notations for complex number. Now we can consider a complex number as a point as well as a vector. So complex number, in the previous slide we have studied that a complex number can be written in ordered pair notation, and all ordered pairs lie on a plane. So how could you plot a point on a plane? That is very simple. For example, if we want to plot a plus b iota, so a plus b iota is actually a comma b in ordered pair notation. So a comma b, this is the real part. This real part will be taken along x-axis, and b, the imaginary part, will be taken along y-axis. and producing this A vertically upwards and producing this B horizontally towards that side. The meeting point of these two is A plus B iota, or we may say that this is A comma B. So that is there is a complex number as a point, and this point lies on xy plane. Similarly, if we plot a vector from the origin towards that point, so that vector is called the position vector of this complex number. So that will be the vector notation for complex number. We have plotted a vector which shows the position of this complex number in the xy plane. So this vector is actually A plus B iota. It means that the component of this vector along x-axis is A, and the component of this vector along y-axis is B. So that is complex number as a vector. For example, we are given complex numbers 4 plus 3 iota, minus 4 plus 3 iota, minus 4 minus 3 iota, and 4 minus 3 iota. These are 4 complex numbers, and we are asked to plot these 4 numbers as points and vectors. So here we are. These are x and y axis. This point 4, we can write this point 4 plus 3 iota is 4 comma 3. 4 comma 3 lies in the first quadrant. So along x-axis we will be taking 4 units, 1 2 3 4. Along y-axis we will be taking 3 units, and producing these two, that is 4 plus 3 iota. Minus 4 plus 3 iota, x is negative and y is positive, so that is actually second quadrant. So in second quadrant we will take x minus 4 units, minus 1 minus 2 minus 3 minus 4, and y 3 units, 1 2 and 3, and producing these two to get minus 4 plus 3 iota. Similarly, minus 4 minus 3 lies in the third quadrant, so that is minus 4 and there is minus 3, that is minus 4 minus 3 iota, and the last one is 4 minus 3 iota. So 4 minus 3 iota will be in the fourth quadrant because x is positive and y is negative. Along x-axis we will be taking 4 units, positive 4 units, plus 1 plus 2 plus 3 plus 4, and y is minus 3, so minus 1 minus 2 minus 3, and producing these two to get 4 minus 3 iota. So that is the plot of these 4 complex numbers as points. These are points actually on xy plane. And whenever we draw vectors from the origin towards those 4 points, so we'll be getting this figure. So that is complex numbers as vectors. Anyways, these are the techniques to plot complex numbers as points and complex numbers as vectors. Now in the coming slide we are able to study the complex plane. What is a complex plane? For example, there is a complex number z, a plus b iota, and we represented this complex number as a vector. So the component along x-axis is a, and the component along y-axis is b. Because this a is the real part of z and a is taken along x-axis, so x-axis is called the real axis for this complex number. and b is imaginary part of this complex number, and b is taken on y-axis. So that's why y-axis is called imaginary axis for complex numbers, and that is the real part of z. B is the imaginary part of z. This diagram which we have represented this complex number as a vector is called Argand diagram. Whenever a complex number is represented as a vector, so the diagram thus obtained is called Argand diagram. In this slide we will study that how many operations can be performed on complex numbers. The first one is the equality of complex numbers. For example, we have two complex numbers, a plus b iota and c plus d iota. These are two complex numbers. These two complex numbers are said to be equal, that is, this number is equal to this number. This equality holds when the real part of these two complex numbers are equal and imaginary parts of these complex numbers are equal. So two complex numbers are said to be equal whenever their real and imaginary parts are equal to each other. Secondly, how could we perform addition and subtraction of complex numbers? Let's say one complex number a plus b iota is denoted by z1, and second complex number is denoted by z2, c plus d iota. Then the addition of these two complex numbers or subtraction of these two complex numbers are just like that, replacing z1 by its own value plus minus z2 by its own value. Now how could we add or subtract? Adding, subtracting the real parts plus adding, subtracting the imaginary parts. These two are imaginary parts. Taking iota common from these two, we will be left with b plus minus d. So this is the technique to add or subtract complex numbers. Similarly, multiplication of complex numbers. Let's say these two are the complex numbers. So how could we multiply these two complex numbers? z1 into z2 means this number into this number. There is a simple multiplication. Multiply this first number with these two to get ac plus ad iota. Then multiply this second number with these two, bc iota plus bd iota square. So that is iota square. Now in the coming step, we will replace iota square by minus 1, and in this step, combining the real parts, those parts we do not contain iota are called the real parts. So ac is the real part, and minus into plus is minus. Minus bd is the real part, and that is the imaginary part. This is again the imaginary part. Taking iota common in these two to get ac minus bd plus iota is common in these two. So that is the multiplication of two complex numbers. A simple multiplication is there. What is the geometrical interpretation of sum and difference of complex numbers? That is a diagram which shows the sum of two complex numbers. For example, that is the first complex number z1 along with vector notation, and that is the second complex number z2 with the vector representation. Now completing this parallelogram, that is the parallelogram. So the largest diagonal, this is the largest diagonal, and that is the smallest diagonal. This diagonal between z1 and z2 is actually the sum of these two, z1 and z2. The diagonal which is between z1 and z2 is the sum of z1 and z2, and the difference is z1 minus z2. So what is z1 minus z2? That is the diagonal, that diagonal from z2 to z1, not from z1 to z2, but from z2 to z1. If you see here, we are going to find z1 minus z2, so that will be the vector from z2 to z1. That is the difference of two complex numbers. So the sum is actually the diagonal of the rectangle between z1 and z2, and the difference of two complex numbers is actually a vector from the second complex number towards the first complex number. In this slide, we have got question number 1 from your exercise 10.1. The question is plot the point and sketch the vector. We are going to represent this complex number as a point and this complex number as a vector. So we have just studied that this complex number can be written in ordered pair notation as 2, 3. Now 2, 3 is a point in which the first component is positive and the second is also positive. So this point lies in the first quadrant. Both are positive. So how could we plot this point? Taking 2 units along x-axis, 2 units along x-axis and 3 units along y-axis, and joining these two, that is 2, 3. So that is the point notation for this complex number. Now what is the vector? Draw a vector from origin towards that complex number. That is the vector notation, I mean the Argand diagram of this complex number. And so for example, if this imaginary part is 0, so will be taking only 2 units along x-axis, so this point will be here, and draw a vector on the axis up to here. If this real part is 0, so we will be taking 3 units along y-axis only, so that point will be there, and draw a vector from here up to there is the Argand diagram for that point. Anyways, that is the technique to plot a complex number as a point and sketch it as a vector. In this slide, we are going to study the notation, question number 2. The question is, express each part of question 1. That question 1 is of exercise 10.1 in ordered pair form. We are giving this number 2 plus 3 iota, and we need to write this number in ordered pair form. So the ordered pair form of this number is 2, 3, and the ordered pair form of -4. -4, it is real, so imaginary part is 0. We can write -4 as -4 plus 0 and 2 iota, and in ordered pair notation this number will be written as -4, 0. Similarly, -5 iota, that is the imaginary part. The real part is 0 here, so this number can be written as 0 minus 5 iota, and the ordered pair notation is 0, -5. Question number 3 of exercise 10.1. we need to find the values of x and y, and equation is given to us. This equation is given to us, and we are asked to find the values of x and y. We see here that this complex number is already in real and imaginary parts, and the right side is also real and imaginary part. So comparing the real part, x plus y is equal to 3, and comparing the imaginary part, x minus y is equal to 1 here. So comparing real imaginary parts, x plus y is 3, and the imaginary parts, x minus y is equal to 1. So we obtain these two equations. We are going to find x and y. So whenever we add these two equations, y will be cancelled out, and x plus x will be 2x, 3 plus 1 is 4. Dividing by 2 to get the value of x, x is 2. Now put the value of x in one of these two equations. For example, I am putting this value in equation 1. So replacing x by 2 in equation 1, 2 plus y is equal to 3, and hence y is equal to 3 minus 2, so y is equal to 1. So the solution is x is equal to 2 and y is equal to 1. So that is how we find the values of x and y. We are going to compare real and imaginary parts on both sides of the equation. In this slide, question number 4 of exercise 10.1, we are given two complex numbers, z1 and z2. z1 is 1 minus 2 iota and z2 is 4 plus 5 iota. We need to find z1 plus z2. That is a very simple operation. We have recently studied that how could we add two complex numbers. So z1 plus z2 means this plus that, this plus that. How could we add these two? Adding the real parts and adding the imaginary parts. So that will become 1 plus 4, just like that, and minus 2 iota plus 5 iota, just like that. 1 plus 4 is 5, and minus 2 iota plus 5 iota is 3 iota. So this is the value of z1 plus z2. And second part, we need to subtract these two complex numbers. So replace this positive sign with negative 1. How could we subtract two complex numbers? Subtracting the real parts, 1 minus 4, 1 minus 4, and subtracting the imaginary parts, minus 2 iota minus 5 iota. So minus 2 minus 5. 1 minus 4 is minus 3. Sorry, this iota is extra here. So here we are. 1 minus 4 is minus 3. Minus 2 minus 5 is minus 7. That is actually minus 7. Minus 3 minus 7. That is the second part. Similarly, question number 5 asks us to solve the given equation for z. Solve for z means to find the value of z from the given information, from the given equation. That is the first part of question number 5. From this equation, we need to find the value of z. How could we find the value of z? Shifting this term towards that side, that is positive, so that will become negative. So we see here z is equal to 3 plus 2 iota minus this whole bracket. Now multiplying minus inside to get, or we may say that we are going to subtract these two complex numbers, 3 minus 1 plus 2 iota minus minus plus iota. So 3 minus 1 is 2, 2 iota plus iota is 3, so z is equal to 2 plus 3 iota is the solution for this complex equation. So that is the question number 5. A very simple question is there. Similarly, question number 8 asks us about the values of k1 and k2, and equation is given to us. We see here that how could we find the values of k1 and k2? There are two unknowns, so we need two equations. And the previous question number 5, we have only one variable z, so we need just one equation. So how could we find two equations from this equation, single equation? We need to compare the real imaginary parts. So first of all, we are going to rearrange this side to separate real and imaginary parts. We have multiplied k2 with 1, so that is k2, and k2 with iota is k2 iota. Now that is first of all we need to write this real part because iota is missing here, so that is the real part, and taking iota from these two to get k1 plus k2 iota. And just look at this thing, we can write this 3 minus 2 iota is 3 plus minus 2 and 2 iota. Now comparing the real imaginary parts, k2 is equal to real, k2 is equal to 3, so that is the value of k2, and k1 plus k2 is imaginary, which is equal to minus 2, so k1 plus k2 is equal to minus 2. Replacing k2 by 3 here, k2 by 3 here, and shifting this 3 towards the right side to get k1 is equal to minus 5. So that is the value of k1. A very simple question. Similarly, in this slide we need to prove some special identities. The first identity is imaginary part of iota z is equal to real part of z. Z is actually a complex number, so this complex number is not given to us. We need to take this complex number, a general complex number. Say z is equal to a plus b iota, or we may say that z is equal to x plus y iota. You can use a, b, x, y, c, d, whatever you use for complex number, but the most important thing to take real and imaginary parts. So let us take a complex number z, say a plus b iota. And what are the requirements of this equation? We need to find the real part of z, so that is actually z, so the real part of z is actually a, so real part of z is equal to a. That is the answer for right hand side. That is equation number 1. Now we need to find iota z. Find iota z and then its imaginary part. So iota z means multiply this equation with iota both sides. Iota z is equal to iota times a plus b iota, and multiplying iota inside, a iota plus b iota square. But we know that iota square is minus 1, so there is minus 1 into b, and plus minus 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 b, so that is the answer for iota z. But we write a complex number in the form of real and imaginary. This real part will be written first, minus b, and plus a iota will be written second, minus a plus minus b plus a iota. This is the answer for iota z. So iota z is minus b plus a iota. We need the imaginary part of iota z. So the imaginary part of iota z is which one? Minus b or a? A, that's okay. A is the imaginary part. So imaginary part of iota z is a. That is equation number 2. So we see here that real part of z is a, and imaginary part of iota z is the same a. So from equation 1 and equation 2, real part of z is equal to imaginary part of iota z. So that is the proof of this equality. And b part, we need to prove that real part of iota z is equal to minus imaginary part of z. So proceeding in the same way, z is equal to a plus b iota. We need to find minus imaginary part of z. So imaginary part of z is actually b, minus imaginary part will be equal to minus b. So minus imaginary part of z is minus b. That is equation 1. And right side, for right side, we should calculate iota z in this fashion. That is iota z, and then we will take the real part of iota z. That is actually iota z. What is the real part of this iota z? That is actually minus b. Anyways, so we have calculated iota z in the same fashion, this one, and the real part of this iota z is minus b. So real part of iota z is minus b. That's equation 2. So we see here that minus imaginary part of z is minus b, and real part of iota z is again minus b. So it means that real part of iota z is equal to minus imaginary part of z. So that is the proof of the second part. Question number 23 says that for any positive integer n, prove that iota power n will be 1, r minus 1, r iota, r minus iota. If we take n, a positive integer, and replace n here, so the answer will be either 1 or minus 1 or iota or minus iota. We are going to prove this equality. So as n is a positive integer, what is positive integer? 1, 2, 3, 4 and so on. So the set of natural numbers is actually the set of positive integers. So that is the set of positive integers. Now we need to replace n by 1 here, and then look at the answer. Replace n by 2 here, and look at the answer. Replace n by 3 here, and look at the answer. Replace n by 4 here, and look at the answer. So first of all, whenever we replace n by 1 here, so iota power n will be equal to iota power 1. Iota power 1 means iota. So iota power n answer is iota for n is equal to 1. Secondly, when we replace n by 2 here, so that will be iota power n becomes iota square, and we know that iota square is minus 1. So the answer is minus 1 whenever n is equal to 2. Whenever n is equal to 3, so iota power n becomes iota power 3. Iota power 3 can be written as iota square into iota, but iota square is minus 1, so minus 1 into iota is minus iota. So whenever n is 3, the answer of iota power n is minus iota. Similarly, whenever we take n is equal to 4, iota power n will become iota power 4. This 4 can be written as iota square whole square, but iota square is actually minus 1, so that is minus 1 whole square, and minus 1 whole square is actually 1. So whenever n is equal to 4, the answer of iota power n is 1. Whenever n is equal to 5, then iota power n becomes iota power 5. Iota power 5 can be written as iota power 4 into iota, but from the previous step, iota power 4 is calculated as 1, so replacing iota power 4 by 1, so that is 1 into iota is iota. So you see here the answer is repeated. This is iota, that is iota. So whenever we take n is equal to 6, we will get minus 1. Whenever we replace n by 7, we will get minus iota. When we replace n by 8, we will be getting 1, and so and so, and the repetition will be there. So from here we can say that whenever n is equal to 1, don't see these numbers, whenever n is equal to 1, the answer of iota power n is, whenever n is equal to 1, the answer of iota power n is iota. Whenever n is equal to 2, don't see at these numbers, whenever n is equal to 2, the answer of iota power n is minus 1. Whenever n is equal to 3, the answer of iota power n is minus iota. And whenever n is equal to 4, the answer of iota power n is 1. So the answer of iota power n is 1. So that is, and now after whenever you replace n is equal to 5, the answer of iota power n is iota, this number. So just look at that, 1 2 3 4 then 5, repetition starts, 5 6 7 8, then 9 10 11 12 13 14 15 16. Similarly, after 16 we will be getting here 17 18 19 20 and so on. So these answers will be repeated for all those values. So therefore the answer of iota power n is one of these 4 numbers for any positive integer n. So that is the proof of this question. The next topic is complex conjugate, that how could we find the conjugate of a complex number. Let's say z is equal to a plus b iota is any complex number. The complex conjugate of z, which is also called the conjugate of z and which is denoted by z bar, or we may say that z conjugate, is defined as z conjugate is equal to a minus b iota. What does it mean? It means that you need to change the sign of imaginary part, not the sign of real part. So changing the sign of imaginary part results the conjugate of that complex number. In words, z conjugate is obtained by reversing the sign of imaginary part of z. What is the geometrical representation of the conjugate of a complex number? That is, say the complex number z, whose real part is a along x-axis and b along y-axis. So that is a plus b iota, which can be written in ordered pair as a comma b. If you look at this z conjugate in ordered pair can be written as a comma minus b. What is the difference between these two? The sign of imaginary part is different. Real part is the same. It means that the real part along x-axis, which is along x-axis, is the same, but the sign of imaginary part, which is along y-axis, changes. So if that is plus b, so that will be minus b. So we see here the conjugate of a complex number is the reflection of complex number and x-axis. So geometrically, z conjugate is the reflection of z about the real axis, which is actually x-axis. So the geometrical representation of a complex number, the conjugate of a complex number, is actually the reflection of the original complex number, and the real axis are in the x-axis. Example of complex conjugates: if z is 3 plus 2 iota, its conjugate will be 3 minus 2 iota. If z is minus 4 minus 2 iota, its conjugate will be minus 4 plus 2 iota. Don't change the sign of real part, just change the sign of imaginary part. If z is imaginary only, if z is iota, so its conjugate will be minus iota. In this last example, we see here that z is real number, not imaginary number, so its conjugate will be the same as given, the 4, because there is no imaginary part for which we change the sign. So if z is real, then its conjugate will not be changed. Z is 4, so its conjugate will be 4. If z is 5, its conjugate will be 5, and so on. The next topic is modulus of a complex number. For example, that is a complex number a plus b iota. Its modulus is denoted by z absolute or z modulus, and z modulus will be equal to the square root of the sum of the squares of real part and imaginary part. Square root of a square plus b square. The square root of the sum of the squares of real part and imaginary part is actually the modulus of the complex number. For example, we need to find the z modulus for this complex number z. So the modulus of this complex number z is the square root of the square of minus 3 plus is there plus the square of 4. We don't write iota here, remember that. Don't write iota here. You see here, this is only b, not b iota. So that is 4 square. Minus 3 square is 9 and 4 square is 16, that is 25, so that is 5. So that is how could we find the modulus of a complex number. That is an example that for any complex number z, if you multiply complex number with its conjugate, then the answer will be the square of its modulus. That is a very popular result, maybe included in MCQs, that z into z modulus is equal to z square, the modulus of z square. So let's say take a complex number z, a plus b iota or c plus d iota or x plus y iota. We need three things here. We need z, its conjugate, and its modulus. So that is z, its conjugate is a minus b iota. Now we need z modulus. The modulus of this z is a square plus b square, the square root of this square, and we need the square of modulus. So that is the modulus of z. So its square will be equal to a square plus b square. That square root will be removed because of square. So that is equation 1, which is actually right hand side. And for left hand side, we need to multiply z with its conjugate. So multiplying z with its conjugate, that is z, a plus b iota, and that is z conjugate. Multiplying these two, a plus b into a minus b is a square minus b square. B is actually b iota, so b iota square. Now from here, that is actually b square into iota square, but iota square is minus 1. So that is minus 1, and minus minus plus, so that is a square plus b square, that is equation 2. From equation 1, the square of modulus is a square plus b square, and from equation 2, the product of z with its conjugate is the same, a square plus b square. So from equation 1 and 2, the square of the modulus of z is the product of z with its conjugate. We can prove this result by replacing z by minus z, and let me write here. We have proved in this example that z into z conjugate is the square of its modulus. You can prove that the product of any complex number with its conjugate can be equal to the modulus of minus z square, and similarly the square of the modulus of its conjugate. Z into z conjugate is equal to all these three. You can prove that, and that is your assignment, to prove that z into z conjugate is equal to the square of the modulus of minus z. What does it mean? Find minus z from here, multiply both sides by minus sign, so minus z will be equal to minus a minus b iota, and then take its modulus and then take its square, that will be the same, a square plus b square. Similarly, z conjugate, that is z conjugate, find the modulus of z conjugate, the modulus of Z conjugate will be equal to square root of a square plus into minus b whole square, so that will be the same a square plus b square. So that is very popular result and may be included in MCQs. And this slide we are going to study the properties of conjugate. For example, for any we are given two complex numbers z1 and z2. The conjugate of the sum of z1 and z2 is equal to the sum of their separate conjugates. Similarly, this result holds whenever negative sign is there, and this result holds whenever multiplication is there, and the same result holds whenever division is there. What does it mean? Whole conjugate is equal to separate conjugates. All these four results mean that. And the last one is double conjugate of Z. The double conjugate of Z is again Z. You can verify this result by taking Z is equal to a plus b iota. So whenever Z is equal to a plus b iota, its first conjugate will be a minus b iota, and its second conjugate will be a plus b iota, which is actually Z. So these are the properties of conjugate. In this slide we are going to prove that half of the sum of Z and its conjugate is equal to the real part of Z. Z is actually a complex number. So take any complex number Z, let's say Z is equal to a plus b iota, and find the real part of Z for right hand side. So the real part of Z is actually a. So that is the answer for right hand side, which is equation number 1. Now we need Z plus Z conjugate. For this purpose we need to find Z conjugate, and then taking this left hand side, 1 by 2 Z plus Z conjugate. So 1 by 2 Z, that is actually Z, a plus b iota, and Z conjugate is a minus b iota. We see here that that is plus b iota and that is minus b iota. So cancelling these two, we will obtain a plus a, 2a. Now 2 to cancel here, so we are left with a. That is the answer for left hand side, which is a. That is equation 2. Now just look at equation 1 and equation 2, both are same. So it means that real part of Z is equal to 1 by 2 Z plus Z conjugate. B part, that is the same with the negative sign over there. Iota is added here, and this side is replaced by imaginary part of Z. You can solve this question in this fashion, that is Z. We need imaginary part of Z, so imaginary part is b actually, that is equation 1, which is actually right hand side, and then find its conjugate, and taking the left hand side, 1 by 2 iota, this is Z, and that is the conjugate, multiplying minus n side, so minus a minus minus plus b iota, minus a plus a cancel, b iota plus b iota is 2b iota, so that is 2b iota. 2 to cancel, iota cancel, b into 1 is b, so the answer of left hand side is b, and the answer of right hand side is again b. So from equation 1 and equation 2, the result is proved. Now that is the slide which is a bit important for your examination point of view. This question number 22, section 10.2, a question is there that prove that Z is equal to Z conjugate if and only if Z is a real number. What does it mean? Z is equal to its conjugate if and only if Z is a real number. So this statement means that if means that we need to take this side true and to prove Z is a real number. only if means take this side true, that z is a real number, and try to prove that z is equal to z conjugate. This is the meaning of if and only if. This is called necessary and sufficient condition. So we need z and its conjugate. Let's say z is a plus b iota, so its conjugate is actually a minus b iota. So starts from f. F means implies. Taking left side true, this left side true, and prove that z is a real number. So let's say z is equal to z conjugate. This is true. We have to prove that z is real number. So as z is equal to z conjugate, it means that a plus b iota is equal to a minus b iota. Shifting these two towards that side, so that will be equal to minus a, and that will be equal to plus b. Minus a plus a cancel, and b iota plus b iota is 2b iota. Dividing by 2 iota, we get b is equal to 0. Now we need to show that z is real. As z is a plus b iota, replacing b by what? Replacing b by 0. So whenever b is 0, so that will become a plus 0, so which is a. So z is equal to a, and we see here that this z is actually real. There is no imaginary part, so z is real. So z is real whenever z is equal to z conjugate. So the first part, direct part, is proved. The converse part is we need to take this side true. We need to take only if means take that side true. Let's say z is a real number, that is z is a real number means z is equal to a. We will prove that z is equal to z conjugate. Now as z is equal to a real number, we need its conjugate. So the conjugate of z is the conjugate of a. As this a is real, so the conjugate of real number is the same a. So z conjugate is again a. So from equation 1 and 2, these two answers are same. So z is equal to z conjugate. So from equation 1 and 2, z is equal to z conjugate. So the new idea in this question is we need to understand if and only if. F means take this side true and try to prove this side. Only if means take this side true and try to prove that side. This statement can also be read as necessary and sufficient condition. Now in this slide we need to study the division of complex numbers. Let's say z1 is a plus b iota and z2 is c plus d iota. Its division is its quotient is z1 by z2. z1 by z2 means a plus b iota divided by c plus d iota. Rationalizing the denominator, multiplying and dividing the conjugate of denominator, which is c minus d iota. So we are going to multiply this division by c minus d iota, multiplying and dividing. Multiplying a with c and a with d, then b iota with c and b iota with d iota to get upstairs here. And denominator is a plus b into a minus b is a square minus b square. Instead of b, d iota is there. And now just look at this thing, combining the real parts. AC is the real part. Iota square is actually minus 1. So whenever iota square is replaced by minus 1, minus minus plus, we will be getting here plus bd, and plus bd is real part, so we have written plus bd along with AC, and that is minus AD iota plus BC iota. divided by c square. Iota square is minus 1. Minus 1 into minus is plus d square. Now from here, taking minus iota common from these two, whenever we take minus iota common, we will be left with AD minus BC. Now we will split this fraction into real and imaginary parts from here. This is real part divided by c square plus d square minus imaginary part divided by c square plus d square. So that is the quotient of two complex numbers. So whenever we find the quotient or division of two complex numbers, the idea will be that we will multiply and divide by the conjugate of denominator. In this slide, we need to express this complex number, this division, the division of these two complex numbers into a single complex number. So how could we? We need to take this division and multiply and divide it by the conjugate of denominator, which is 1 plus 2 iota. Then multiplying upstairs to get upstairs this one, and a minus b into a plus b is this one, and simplifying, that is 3. Iota square is minus 1. Minus 1 into plus is minus 8, which is real, so minus 8. 6 iota plus 4 iota is 10 iota, and 1 square is 1. Iota square is minus 1. Minus into minus is plus. 2 square is 4. 3 minus 8 is minus 5. Splitting into real and imaginary parts, minus 5 by minus 5 plus 10 by 5 iota, cancelling these two and these two to get minus 1 plus 2 iota, which is in a plus b iota form. Now that is the same question. We need to find the real part of the quotient of z1 and z2 and imaginary part of the quotient of z1 and z2, where z1 is this number and z2 is this number. First of all, we need to find z1 by z2. z1 by z2 means this divided by that. Now simplifying this, multiplying and dividing by the conjugate of denominator, this one, that is the same process. Multiplying these factors, we will be getting this one. Denominator a plus b into a minus b is that one. Replacing iota square by minus 1, so that will become plus. So you'll be getting x1 x2 plus y1 y2, and taking minus iota common from these two, minus iota is common, we are left with x1 y2 minus, because we are taking minus common, y1 x2, and splitting this number into real imaginary from here, this by that minus this by that into iota. So that is the answer of z1 by z2. So the real part of z1 by z2 is this one, and imaginary part of z1 by z2 is this one with negative sign.